Alright, I think I'm going. Alright guys, let's get started here. So here's your function. So before we do any calculation, let's just look at it holistically. So look at it like vegan style, you know? So just what does this graph look like? It's like this. Now, when we answer this question, it gets us some very interesting information about how steep is this graph, like right here. How steep? Yeah, it seems pretty steep. It's not really obvious because, I mean, if you're in the habit of drawing it like that, you might go, I don't know, is it a slope of 1? Who knows? There's also interesting stuff that you learn about in calculus, like fun fact of the day, like you ever look at the sine curve? Like
On
that?
my own time? No.
So I've seen it. How steep is this graph at the origin?
Steep.
Turns out it's just 1. Okay, so just fun fact of the day. The sine graph has a steepness of 1 at the origin, but then like it's kind of funny if you just look at this little neighborhood of the sine graph, you might go, oh, that neighborhood looks kind of like a cube root function, doesn't it? Yeah. Sort of, kind of.
Yeah.
How steep is the cube root function at the origin? Stonks, infinity. Turns out it's infinitely steep. So it's kind of weird to get this weird result of the sine graph has a slope of 1 at the origin, and the cube root function, which kind of bears some similarity, sort of, kind of, has an infinite slope. So how does that work out? So anyway, there's this guy. So what we know, though, if this is the graph of f, then it's a nice marker. Okay, so what's the first thing we know 100% sure? What has to be happening over here? Nothing. This is no man's land. Because this function is not even defined. How can we have like a limit or a tangent line or anything if the function doesn't even exist over here? And then so just generally speaking, what's happening to these slops as we move across the curve?
They're getting steeper.
Yeah.
They're getting less.
They get less steep. So they're all positive. Look, that's obvious. They're always positive, and they start off pretty steep, and they get less steep. Okay. Now the question is, what we don't know is what's happening actually at 0. So there's kind of like a question mark here at 0, but we know that generally speaking, it does this. It has to decrease. Make sense?
Yep.
It has to always decrease, but always stay positive. Now, if you think about that, in order to always decrease and always stay positive, you have to be kind of curving down and leveling out towards 0. So this is the mystery, though. So let's get into the math of it. So the limit definition is that the derivative is the limit of the rise over run. So the rise over run is f of x plus h minus f of x over h. Okay. So let's apply our formula. Make sure you're using valid limit notation, okay? You saw me yesterday, I messed it up once. I forgot to write limit, so please just make sure you have, if you're saying that this limit is equal to something else, most of the time it's this limit is equal to some other limit. You're not gonna get rid of the limit notation until the very end, okay? So f of x plus h is, I saw in some of your guys' papers, you had this, a lot of you guys had it set up perfectly, so kudos if you had this. This is where most people get stuck.
Yes.
Okay. That's f of x plus h. That's f of x, and then it's all divided by h. Now, right now, you can't plug in 0 because you'd be dividing by 0. You can't do that. More specifically, if you plugged in 0, you'd have root x minus root x, 0 over 0, which is indeterminate. So we're like, okay, we got it. It's indeterminate. What do we do? Who thinks they know what I'm going to do right here?
Skibbity
boop bop, exactly. Gonna use a conjugate. Okay, so the conjugate is this. There's always some confusion on the use of this. The confusion often is people going, oh, do I go x minus h? I have thing minus thing, so the conjugate is thing plus thing. Apple minus banana, you go apple plus banana. You don't try to throw a negative into the apple. Don't make sense. Okay. All right. So this is kind of some kind of trickery here. What does this actually do? Well, like a lot of things when you're doing algebra type stuff, it's sort of not really a Hail Mary necessarily, but you're kind of just like hoping something happens. You say, well, I've done this before. It sometimes helps out. Let's see what happens. I know it's gonna eliminate all the radicals. That's kind of the motivation for it. Is you go like, if you do this, it'll get rid of all the square root symbols on top, which is nice.
The radical left.
So you have a minus b times a plus b, basically, right? So you're gonna have a squared. What's a squared? X plus h. So a minus b times a plus b, so you get a squared minus b squared, like that. So does everyone understand getting from there to there? Top times top. B's. Now the bottom, let's just keep the h separate, because we're hoping to be able to cancel him. Let's keep him out there. So that times that is just going to be that. And then you rejoice because you say, oh, yes. X minus x is 0. And now I have just h on top. So now I can just be careful when you cancel these out. H divided by h makes 1. So you're kind of left over with like a 1 up top. So what's left over on top is a 1, and on bottom we have square root of x plus h. Okay, now we can finally get rid of the limit because we're done. Can I now plug in 0 for h? What's on bottom? So I know there's a 1 on top. Yeah, so if I plug a 0 in here for h, I've got a root x plus a root x. I brought my props today. There you go. People at home, there's their props. 1 root x plus 1 root x makes 2 root x. That's educational. 2 root x. There's your answer.
Ooh, that was a lot of work.
That was a lot of work.
A lot.
Yeah.
Trey's reading like a 400-page book about argumentation. And then we do like a 5-minute proof. That was way too much, man. I mean, I just got done reading Bertrand Russell's History of Western Philosophy, but that was a little bit too much. I mean, pushing it. Okay. So anyway, we now have an answer to this question, because what actually happens as x approaches 0? Yeah, there's actually an asymptote on this derivative function. And so this curve, very interestingly, it turns out that there actually is no derivative. So f prime of 0 is undefined or does not exist. Okay, right? So that question before of, is there a derivative there? No, there's no derivative there. And then moreover, what's the derivative at like a really tiny x value? Well, it's going to be arbitrarily large. So you can get, if you want a slope of 10 billion on this curve, you can find it. Just find the right x value that produces 10 billion on here. It would be 1 over 20 billion squared if you're, that would be the x value. Okay, so questions? Questions? Yes, David.
So when you went from the 1 over root x plus h plus x, you just substituted 0 in for h, and then let's say you got to root x.
This last step? Yep, so we put a 0 in here. And so the intermediate step would have been that this becomes 1 over, so that's me really showing the work there is, yeah, just replacing the h with a 0, because now it's fine. If I do that, I'm not dividing by 0 or anything. So then I have root x plus root x, which is 2 root x. Make sense?
So, hold on. When you're saying finding X values undefined, do you just put zero or do you say when it's less than zero? Or right,
The last one. So yeah, so the follow-up question on this problem is, first it's asking us to plug in a couple of X values. That's pretty trivial, right? You just plug them in. So what's the derivative when X is, say, 4? Plug a 4 in, you get a quarter. What about when X is 3? You get 1 over 2 root 3, okay? That's just basically making sure we all understand how simple is it to evaluate a derivative. That's using fancy words, evaluate meaning just, what is the derivative when X is 3? How steep is this tangent line when X is 3? What's the slope here? Well, the slope would be, in this case, 1 over 2 root 3. Okay, you literally just plug 3 into the derivative. Make sense? What's the derivative when X is 1? 1/2. Easy peasy, right? And then the question of when is the derivative undefined or it does not exist, it would be any X value less than or equal to 0. Does not exist. Okay, let's move on. So, like before, try to set it up. I'll give you a minute to get it. Oh, sorry, the function, just to start off. It's the 1 over x function. Which we already have a pretty good idea of what's going to happen there. You have f looks like this. So yesterday or the day before, I think it was the day before. No, it was yesterday, wasn't it? The derivative would have to look something like this. Just based on, just purely looking at slopes. Negative slope, they're getting steeper. Negative slope, negative slope, negative slope, they're getting less steep. And so you can kind of just view the connection between their behavior. So yeah, so start it off. And by the way, hopefully the first part is fairly straightforward for you by now. F of x plus h is just, you replace the x in the function with x plus h. And then f of x is just f of x. And then the bottom is h. Now here's the fun part. This is the fun part of any question like this, is what's the first step? That's close. Conjugate is, so using the conjugate is going to be a very good strategy most of the time when there's radicals. If there's no radicals, then we usually don't employ that conjugate technique. Although I would say it's kind of related to this, because when you use the conjugate technique, you're effectively multiplying the fraction by, what was the overall value of that red thing before? What was that? 1. Ghost face.
Why is it plus this time instead of?
Just testing you, Ave, obviously.
I was so confused.
Thank you. That's a good question.
when you multiply by like.
What?
Bottom, the top, like.
We're going to multiply, so firstly, we're going to multiply by 1. That's a very common theme. So we're going to multiply this by 1, and then you had a good idea, Rafe, which is, I mean, you got to think about shampoo, right? No more tears, Johnson & Johnson. No more tears. We asked the question. We got fractions inside a fraction. That's cringe. Yeah, that's tears. That's sad.
That's tears.
That makes you sad. How can we? Just ignore the bottom for a second. What could I multiply this by that would eliminate all the fractions? Well, he wants to get multiplied by x plus h, right? And he wants to get multiplied by x. So let's multiply the top by x and x plus h at the same time. How do we feel about that?
Sure.
Well, do you agree that
Yeah, no, I agree.
this times this, what are you gonna get when you go this times this? What's left over? X would be left over, right?
And now they're gonna get X plus H.
Very good. Are we okay with that?
Yes.
Okay, now, I can't just multiply this thing by this.
You have to multiply over it.
It has to be 1. So this red thing that I'm writing has to be equal to 1. So let's do it. Let's make sure there's no confusion over this. Does everyone understand why this term times this top here? When I multiply this by this, the x plus h's would cancel out and you'd be left with just an x. Do we all understand that?
Yes.
And then minus, when you multiply this term by this, the x's would cancel out this time and you'd have an x plus h. But make sure that x plus h is in parentheses or else you'll be making a mistake.
Mistake.
And on bottom, we're just going to leave it as h times x times x plus h. Again, we are hoping to cancel-y out the h. Now we're going to have okay, so on top, we're going to have x minus h, so negative h. And on bottom, we're almost done. We're one step away. Those cancel out. And we get, now we can plug in 0, right? When I plug in a 0, well, the top's going to be -1. Hope that's fairly clear. If I replace the h with a 0 now, I have x times x.
X. One of X.
Then we ask, does that agree with our intuition?
Yes.
Graphically, yeah.
Perfect.
It's actually amazing that it turns out to be such a, I mean, yeah, if you had to guess, what shape is that? You know, this is the most reasonable guess you could make. Without arbitrarily guessing some kind of multiplicative constant or something. But yeah, there we go. Boom. There's the answer. Beautiful. Amazing. Amazing how that works out. All right. Start on the squared one. Or where sorry, let me again clarify. What's f prime of blah? What's f prime of blah? You just plug in those x values. What's the derivative of this function when x is 3? Negative a ninth. Easy peasy, right? What's the only value where the derivative is undefined? 0. There you go. Yes, Elizabeth.
Why is it the answer x squared? Because you still have an h, so wouldn't it be x squared plus 8xh?
Well, remember, this is a limit. This whole time, this is a limit.
Oh, yeah.
So we're hoping, at every step, we're hoping, it's like, you know, a little kid in the car. Are we there yet? Are we there yet? You're asking, can I plug in 0 yet? Can I plug in 0 yet? No. Can I plug in 0 yet? No. Can I plug in now? Yeah. Once you cancel them out, now you can plug it in. Okay, so get that 1 over x squared set up and roll. I think it's the last one.
Wait.
Yay! What? Why don't you guys take a couple minutes? Try to finish this one. It's very similar to the last one. The very last step might trip you up a little bit, but I feel pretty confident that most of you guys already get it. So there's the graph, and you can know in advance my answer needs to be something where it's positive, 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 growing positive numbers. Okay. Negative, 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 negative numbers approaching 0. So it's something like that, whatever that is. So anyway, take a couple minutes, see if we can get it. We'll go over the answer. How are we doing?
Not good.
Not good. But something's gotta come on.
I mean,
Got something? We'll go over it in like a minute.
That was like an answer.
That looks like an answer.
That was.
mm,
That kid was sprinting. Like doing their laps, and then one kid was just breakneck speed. Okay. Sorry, this is very funny. Okay, the first step. Hopefully you got the first step.
maybe.
Because the first step is exactly the same step as the last one we did. You want to multiply by x squared and multiply by x plus h squared.
Okay, got that. Got that.
On top and bottom. Okay, so you got that.
What to do?
Good. That means you recognize the pattern and you're able to apply. That's good. Let's multiply it. So now we have, again, limit as h approaches 0. And so this times that, you'd have the x plus h squareds cancel. You'd be left with x squared. Then you'd have the x squareds cancel on this multiplication, and you'd have x plus h squared. And then on bottom, you have this gross mess here.
Okay, I got that far. That's pretty good.
Made it.
Okay. And then again, you go, can I plug in H yet? No, we haven't cancel anything, so your feeling should probably be, no, you got to get something to cancel out. But you can probably see, oh yeah, I'm going to have an x squared there that's going to let me cancel out, so that's good. So let's do that. You may have, this is the part that maybe didn't occur to you, is you got to expand that.
I know.
That's going to end up being necessary. So kind of like what we did when we took the derivative of x squared, we had to expand a term like this.
Yes, sir. Yes, sir.
Trenton, are you okay over there?
No.
No, yes.
Well, no, I am. It's cool. It's cool. It's cool.
Okay. So now when we do that, think about what's going to be left over on top. And in fact, let's do two steps at once. The x squared is going to cancel the x squared. We can see that. It's pretty clear. And then let's factor out an h. So you have an h times, be very careful here. What's the first term? Negative 2x minus h. So be careful with this minus sign here. So this becomes this. And on bottom we have, now we rejoice. The h is canceling. Oh man, cancely bobancely. Truly transcendent experience. This is what Thoreau was talking about. Cancely wancely. Yeah. To quote Thoreau, that feel when you go into the forest and it be cancely wancely. That's from my favorite book ever. Okay. Can I plug in 0 now?
Sure.
Yes.
Yeah.
Plus 0, wait, wait,
Here?
or no, I see.
Not quite yet.
Ooh,
You can plug 0 in now because you've shown that, okay, we've got the h's canceled. So you don't have to show like every little step. I feel like I'm showing kind of the minimal amount of steps here because otherwise you're, I mean, you can maybe get away with going from here to here, but you're getting into some,
dangerous territory.
unless you're like, you gotta already have the clout. You gotta be rooted. This guy famously wrote a textbook where he just like, he doesn't like explain anything.
How did that sell? How did that?
I don't know. It's
work?
famous because it's so comprehensive. No, it's so thorough. And I don't know, like you'd have to ask someone who's studied it more. Like it's Rudin's the guy, Rudin, and he made a book on real analysis and a book on complex analysis and a book on functional analysis. And they call him, it's like Baby Rudin, Papa Rudin. And I can't remember what the last one's called. Anyway,
God.
but this is a notorious book because it's like one line to understand it. You have to like, he writes one sentence. You got to like kind of do it yourself and figure out what he was talking about. So anyway.
No?
Plug 0, in any case, plug in 0.
Amen.
You get, plug a 0 in here, the top is negative 2x. Plug a 0 in bottom. Let's see, that's a 0 now. So you have x squared times x squared, which is x to the 4th. Cancely-wancely a little bit, and you get the answer. That's a nice answer.
That didn't look like it.
That's pretty.
I don't
Oh, you guys
know
got
about that.
It looked like an answer.
Now does that agree with that?
Yeah.
Yeah, that's okay. How are we doing for time?
It's Wednesday.
It's Wednesday. Okay, we get to go over something very lit. Now you thought you loved the limit definition of the derivative. Wait until you see the alternate limit definition of the derivative. Now that's
The alternate.
the alternate definition.
I guess we're gonna find out, Trinity.
It's of course logically equivalent. It is the same definition, it's just written a different way.
Well, I like my way.
I recently saw something where the person said, they raised the question of like, is math just a whole bunch of like giving names to things?
Yes.
Kind of, yeah.
Just complicated counting.
Yeah, probably. There was a TikTok, this girl's like doing her makeup and she raises the question of like, who invented math? And it got kind of like ridiculed, but also a lot of mathematicians were like, yeah, it's actually like, she's posing an interesting question. Did you guys see that? Anyone see the video or no?
No.
It was, she brings up the question of, she has basically something to the effect of like, I get why you'd say like 2 + 2 is 4, because you have two chickens, whatever. But like, then she raises the question of like, why would, I think the one part of the reason maybe she got teased was she was saying, why did Pythagoras come up with y = mx + b? Like, anyway, but the idea is like, yeah, why would they be concerning themselves with abstract mathematical concepts like before they knew about, say, like germs or had like plumbing, things like that. So like, it was
That's very fair.
it's an interesting question. But those people back then were doing a lot of thinky winkies. Lots of thinky winkies about lots of different things. Huh?
Do they get paid for thinking?
Who?
Like,
Early math.
Oh, like ancient Greece people?
What?
I don't know how.
what did they do?
I think a lot of those thinkers were probably born, not super wealthy, but they weren't born into like a peasant class or whatever.
Oh,
Like,
yeah.
so they probably had the resources to like just spend their time doing whatever they wanted, and they would just thinky winky a lot. I don't know much about ancient Greek culture, but I know they had like what?
Didn't it?
Well, a lot of it got used, I think, for building. My history, I mean, I don't want to give you any wrong information. My history knowledge is very, very lacking. So, okay. All right. So I want to do a comparison here, guys. So yesterday I showed you this one. Okay, here's some wacky function. This is some function f. Y = f of x. And so this is just a review of yesterday. So yesterday we said, say I'm interested in finding the slope at some value x. I bump the x value over to x plus h. I just bump it up by some tiny amount h. I look at the average rate of change, so just rise over run. So like think about this y value is f of x plus h, and this y value was f of x, the original point. And so of course the rise over run, the rise is f of x plus h minus f of x, and what's the run? From x to x plus h is a run of h. And so what you do is you say, okay, do the rise over run, rise over run, and then just take the limit as your run approaches 0. So that's one framework under which you can understand what a derivative means. Alternatively, this is the alternate definition, is you say, this might be a little confusing, hopefully not too confusing. Say some other function. Suppose now you want to know what's the derivative at some value c. What you do is you say, consider all x values in the neighborhood of c. So consider some new x value out here. Okay, he's got a y value. So what are these two y values? His y value is f of, this one's f of x, and then this one's f of c. And you say, what's the rise over run here? What kind of rise over run am I dealing with? Notice it's the exact same concept, it's rise over run. My rise is f of x minus f of c. and my run is x minus c. So now what I do is I say, okay, my rise over run is f of x minus f of c, and my run is x minus c, and I take the limit this time though. You could, I mean, it would be unconventional, but you could maybe make some formulation where you say the limit as this goes to 0, but it's much easier to say the limit as x approaches c. So what happens is I push this x value close to c. So this right here is the what they call the alternate limit definition of the derivative. The big difference is this one you often are looking at, like Sam really focused on just knowing the derivative at a single point. So say you have some peculiar function where I don't really care about getting a general formula for the derivative. I really just want to know what's the derivative at this certain x value. This is typically what you use. So as a quick example, bell might ring, but so for 22, oh, we got time to set up 22. So for 22, all you got to do is notice they give you a function. By the way, we already know the answer to this one, if you think about it. It's asking what's the derivative, given this, what's the derivative at 7? Okay, the answer is what? No, it would be 7. It's going to turn out to be 70, but it's okay. We'll get to this. So the answer is going to be 70. The reason I say we know that is because we showed before the derivative of x squared is 2x. So you might stands to reason that the derivative of 5, if you stretch it by a factor of 5, the derivative should be 5 times bigger. So anyway, what you do is, okay, to do it, we got to do this. This is the word. Got to do it this way. Even if you go, oh, I have some other way of figuring it out. So you got to go, okay, the limit as x approaches, what's my c value here? What's the value I care about? 7. So basically what I'm saying is I got this parabola. At 7, I'm asking the question, here's f of 7. I'm asking to basically take the limit as I approach 7. So I go f of x minus f of 7 over x minus 7. That's the setup. Cool beans? So in this case, my c value, c for care. That's what I care about. Okay. Okay, so f of x was, so this is the limit as x approaches 7. Okay, f of x is 5x squared. F of 7 is, where's f of 7? I'm going to write it like this, 5 times 7 squared. Think about why we want to write it like that instead of writing whatever 5 times 49 is.
It's a big number.
But think about what I can do with this now that I've written it that way for a reason.
Can't see Bobans.
I've written it that way because I want to factor out the 5. So factor out the 5, then factor the x squared minus 7 squared, cancely, plug in the 7. Try to finish the problem and try to finish 23. And we're cruising here. What, George? Cruising.